Section 33.6 Molecular Collisions. This is a very important topic in chemistry because for two molecules to react with each other, they have to first collide with each other. And usually the reaction rate is proportional to the collisional frequency between these two types of molecules. I'll let you watch this YouTube video to see ineffective collisions and effective collisions. The effective collisions have the right collision orientation. The colliding parties have enough energy to overcome the reaction barrier to form the product. Now let's look at this example. Let's say we have two types of particles, 1 and 2. This one has a radius of r1. This one has a radius of r2. Now let's assume this orange sphere of type 1 is traveling at the average speed, v average. And then near the path of the traveling of this orange sphere, we have a total of 8 red spheres. How many of these 8 red spheres will collide with this orange? I don't know. Just imagine this orange traveling to here. And then you have to imagine if there's overlap between this orange sphere, for example, when it arrives this position with this red sphere, again, there is an overlap, then a collision will happen. However, when this orange sphere travels to this position, all right, and then look at this red one, this orange one, imagine at this position, there's no overlap, then there's no collision. So really, we just need to count the number of red spheres that would have any overlap with this orange sphere as it travels in this direction. Mathematically, we need to imagine a cylinder here with a length of v average times dt. So this is the distance the orange sphere travels within this time interval dt. And then the surface or the bottom surface of the cylinder is pi times r1 plus r2 squared. So this is the sum of the atomic radii. This sigma has a name, collisional cross-section area. So we can now look at the red spheres. If a red sphere has its center sitting inside the cylinder, a collision will occur. Now let's look at this sphere. Its center sits outside the cylinder. No collision will happen between this orange and this red one. Same for this and this. All we need to do is to count the number of red spheres with its center sitting inside the cylinder. But then how can we count it? Well, first, if we know the density of those red spheres in the reaction container, and then we can calculate the volume of the cylinder. The volume of the cylinder times the number density of the red spheres will give us the number of these red spheres with its center inside the cylinder. Now, we assumed these red spheres were not moving. Now we need to make a correction. Both the orange spheres and the red spheres move constantly in the reaction container. So you can't just directly use the average speed of this orange sphere. You'll have to take the motions of the red ones into account. Now there are three situations. These two are moving in the same direction, in the opposite direction, with a 90 degrees angle. Also, they can move at some other angles, any other angles between 0 and 180. So if we consider all possible scenarios, we'll get the so-called effective relative speed between these two molecules or two particles. It's this: the average relative speed is the square root of the sum of v1 squared and v2 squared. v1 is the average speed of type 1. v2 is the average speed of type 2. And the average speed is 8 kbt over pi times mass. So we got this equation here. And then we can combine these two by defining this mu. Mu is the reduced mass. By looking at this equation, you may realize 1 over mu is equal to 1 over m1 plus 1 over m2. So again, this is the definition of the reduced mass. 1 over mu is 1 over m1 plus 1 over m2. By looking at this equation, if m1 is much greater than m2, the mu is approximately equal to m2. Why? Because if m1 is much greater than m2, then the reciprocal of m1 is negligible. And therefore, mu is approximately equal to m2. We can rearrange this equation to get mu is equal to m1, m2 over m1 plus m2. Now we can calculate the collisional frequency, this lowercase z12, for each particle of type 1. What's the definition? It's the number of collisions this particle undergoes within this time period, delta t. So within this time period, delta t, now we need to use the relative speed. So the distance this type 1 travels relative to type 2 molecules is this relative speed times delta t. And now we calculate the volume of the cylinder. The bottom surface area is pi times r1 plus r2 squared, and it's sigma. Collisional cross-section area. And this is the volume of the cylinder. And then over here, N2 is the number or the total number of type 2 molecules inside this container with a volume V. So this is the so-called number density. The number density times the volume of the cylinder, we get the total number of type 2 molecules with its center sitting inside the cylinder. And this is the number of collisions between this type 1 particle and type 2 particles within this time interval. So divided by this time interval, we get the collisional frequency over here. So you can see the collisional frequency is proportional to the number density of type 2 molecules. It's proportional to sigma, the collisional cross-section area. It's also proportional to the relative speed. Okay, this is understandable. Over here, if you have more N2 molecules in the same container, of course, there's going to be more collisions. And now over here, if type 1 and type 2 molecules are really big, then of course it's easier to have collisions. Well, imagine in a room you have 100 flies blindfolded and they fly around. The collisional frequency is low. Now if you change the flies to really large birds, they also fly around at the same speed, well, you will observe many more collisions. And also, of course, the collisional frequency is proportional to the relative speed. Now again, the same example, but imagine those birds are not flying at all. Then there's no collisions. If they fly really fast, again blindfolded, you will see more collisions. Again, let's imagine a reaction container. We have N1 type 1 particles and N2 type 2 particles. Now let's focus on the total number of collisions between all type 1 particles and all type 2 particles. We just need to use this Z12 times N1. That will give us the total number of collisions per unit time. However, that's an extensive property. It's proportional to the volume of the container. Again, if we're assuming the number density is constant, and then the larger the container, of course, we have more N1, we have more N2, right? And then we have more collisions per unit time. So we decide to set this variable, uppercase Z12, as the total number of collisions per unit time per volume. And then we have this lowercase Z12 times N1. That's the total number of collisions per unit time, and then divided by V. Now we get this formula as the total number of collisions between all type 1 and all type 2 per unit time per unit volume. And this equation tells us the total number of collisions per unit time per volume is proportional to the number density of type 1. It's also proportional to the number density of type 2. So if you have learned the bimolecular reactions, the reaction rate is proportional to the concentration of type 1 and the concentration of type 2. Now again, if these two molecules are pretty large, you'll observe a higher frequency. And if they move really fast, also you will observe higher frequency. Again, this V12 is the relative speed. It has this formula. It's the square root of 8 kBt over pi mu. N1 over V can be expressed as the Avogadro constant times the number of moles of type 1 over V, and N over V is simply P over RT. So you can also write this N1 over V as a function of the partial pressure of type 1 and temperature. So by looking at this, if I ask you this question, when temperature increases, how does this uppercase Z12 change? It's actually a tricky question. If P1 and P2 are constant, then when temperature increases, although this V12 increases, the relative speed increases, but the number density of type 1 decreases. The number density of type 2 molecules also decreases. And therefore, you will have actually lower collisional frequency. But again, if we hold this constant, and then when we increase the temperature, this Z12 increases. So it's a tricky question. Now let's look at another scenario. Let's just look at the collisions between type 1 and type 1. In this case, we'll have to avoid double counting, because let's say we have two type 1 molecules, A and B. If we use this formula, just C11 times N1 over V, then we imagine this A travels and may collide with B. And then we also imagine B travels. It may collide with A. Therefore, we double counted the collision between A and B. That's why we need to put this 1/2 here to make the correction. So this uppercase Z11 is only 50% of this lowercase z11 times n1 over v. All right, so we got this formula. Again, it's similar to this formula with two changes. This n2 is replaced with n1, and then we introduced 1/2 in front to avoid double counting between the two particles A and B. Again, if A collided with B, we should not count this B collides with A again. Therefore, if we have a reaction container, inside there are N1 particles 1 and N2 particles of type 2. The total number of collisions is this. We have 1-1 collision, 2-2 collision, and 1-2 collision. This formula is the number of collisions between type 1 molecules, the collisions between type 2 molecules, the collisions between type 1 and type 2. And again, this is the total number of collisions per unit time and per unit volume.